Alright, so we start again. Copyright notice is here. We have these slides are from CS230 prepared by deeplearning.ai. Alright, now we were doing object detection. So we had finished all the way until, so we had talked about the difference between classification with localization and object detection. Right. So we had talked about this, that for localization you also need to output a bounding box. What does that mean? If you want to output a bounding box in an end-to-end deep learning algorithm, then what should happen? This should be there in your label as well, right? I cannot output something on which I was not trained on, okay? So I need to have this thing in my label Y as well. So some nodes for softmax and some nodes for bounding boxes. Then we saw how to prepare a training data set for. So if this is the image, all I need to do is mark this bounding box, okay? So how will I prepare this training data set? For this input image, this will be my ground truth or label, okay, what we call as Y. This one is important here. Why is it 0? Because there is no object. No object means none of these three. So 0, and these question marks actually signify that whatever these numbers are, right, we don't really want to pay attention to them. Of course there will be some numbers, okay. We talked about landmark detection, right? In this case it was BX, BY, BH, BW. In cases of face you have a long list of them and so on. Object detection, right? So we were here. What is going on in this? You have so many images. Let's say we are right now trying to detect car, right? Let's keep our life simple by saying there is only one object called car and I am going to detect that one. Is this an easy problem to say whether there is a car in this or not? Yes, classification was easy, right, compared to this one. Now, what we are supposed to do in this case now? How do we prepare the training data set? So this algorithm says you just crop all the car images, okay. So this image has label 1 because there is car in this. This has 0 because there is no car in this. And then given this image, I can run a neural network, in this case a CNN, to classify whether there is a car in this or not. Okay. So you are essentially doing classification only. So you are basically doing classification on images. You take, this is sliding window detection algorithm. So we are trying to do object detection now. So what you have in this case is a smaller window. So if let's say there is a car of size this, so it may not detect it, right? Will this one do? Maybe yes. Assume this is small enough that it will fit in here, okay. Now, so you start running this particular sliding window. So you start running this particular sliding window and now it's a, now it's a classification problem. Why so? See, how many of you are okay with this algorithm? Very simple one, nothing special you are doing. Take this bounding box, put it here, right? And then ask this question whether there is car in this or not. So it's not localization anymore, it's not detection anymore. It's simple classification. Take this box here and then detect whether there is car in this or not. If not, whatever. Yes, no, go next. So take some stride. Look for that area. If there is car or not, you keep on doing this for the whole image, right? So hopefully you will end up having, so hopefully this box will say there is a car, and hopefully this box will also say there is a car. Okay. Now the difference between these three images is that, what is the difference between these three images? Only the size of the window. In the limiting case, my sliding window can be of size 1 pixel. In the extreme limiting case, this side, my sliding window can be of size the image itself. Okay. So that gives me the whole spectrum. What are you looking for? We are looking for a reasonable size of sliding window which is not as small as a pixel and not as big as the whole image itself. So somewhere in between, now this is a hyperparameter, what will be your window size? Okay. And will all window size suffer from one problem or the other? Right. So for example, if I add to my, sorry, let's keep it here only. Right now, let's say we are just detecting cars, right? Let's say you come up with two classes now. One is a car and another one is a tennis ball, right? You can't have a sliding window, when, which suits for both of them, right? So this algorithm will always have major issues. Nonetheless, it allows you to detect objects. More issues with this? So that's a different thing. That has nothing to do with this sliding window, right? That will be a challenge for any other algorithm that you give me. So right now we are talking about challenges specific to this. So if I have two objects of different size and different shapes, I will be in trouble. What else? What will be wrong with, for example, if I am also trying to detect these street lights and my window size is large? This box will also detect, this will also detect the, what is this, traffic light. This one will also detect, this one will also detect. So there will be so many traffic lights. In reality there is just one. Okay. And this can also happen with a car, right? This bounding box may detect a car and then the next one may detect a car as well, even though that is the same object. You increase window size, most likely you will reduce these problems, but you can't say that it is guaranteed or it is up to some extent guaranteed that this will work better than this. So now, in terms of efficiency, which is more computationally expensive? That one. Why? Because for this whole image you are doing more classifications. Right? You are doing more classifications here, then the number of classifications has reduced and the number of classification in these three cases it has minimized here, right? So you will do lesser work here compared to this one. But again, there is a trade-off between window size and this size as well, because just saying more classifications may not mean too much, right? But that's what we can roughly say, that the complexity is kind of increasing in this side. So wait, let me first finish this thing. you know, this will not be strictly increasing, this may not be strictly increasing because you have smaller window size. So the cost of one classification is lesser. In this case you have bigger window size, so the cost of one classification is higher, okay. But you have lesser number of classifications here, more number of classifications here. So this won't be a linearly or whatever, right? There has to be some trade-off. So there will be some window size for which complexity will be best. Yes. Exactly, this has happened. So if you are going to give me just one class, right? So one of them will be missed. Because in the end my sliding algorithm will say it is only classifying. So as we know classification, what does it do? In this image, which, I mean, what is there, right? So in classification, we just output one class. We don't know how to classify things by saying I have two classes in this. Right now we don't know. And softmax, does it help us there? No. Okay. More questions here. Yes. This is fine. So we have converted a detection problem to a classification problem. Okay. Now convolutional implementation of sliding windows. This is a really good idea. Can anyone, and after that I think we should go to, So sliding window algorithm is fine. Now in this case what is happening? So let's talk about an example. This example right now has nothing to do with the sliding window, right? So this brings us to some concept. This is 14 cross 14 cross 3. What will be this? 5 cross 5. See, nothing is mentioned, so this is the normal convolution, right? If it were mentioned that this is depth wise, then we would think. Nothing is mentioned, so this has to be 5 cross 5 cross 3. And then how many filters? How many filters? 16. Okay, so you get this one. Max pool 2 cross 2 gives you 5 cross 5, and max pool does not touch the, so this is fine. This is now fully connected. How many numbers are here? 25 into 16 is 400. So basically these two things are the same. These numbers are just flattened into a vector, right? So flattened into a vector, and you get this. So these numbers are same as these numbers. Now 400 cross 400 weight matrix here, and then you have 400 here, and then how many here? What will be here? We have 4 classes. What were they? Pedestrian, car, motorcycle, and background. Okay, so those things, right? So given an image, we know how to classify. This is good old classification, nothing new here. Okay, so done. Now what happens in this case? What is the difference between these two? I don't understand. It will really help if you can help me out here. Yes? So until here things are same, right? So we don't talk about them. What did you do here? You flattened. What did you do here? You flattened. But in this case you are keeping it as a vector, and in this case you are still keeping it as a volume, right? So this was a volume of size 5 cross 5 cross 16, 400 numbers, still 400 numbers, but I don't keep it as a vector now. I just keep it as a volume. So instead of 5 cross 5 cross 16, these numbers are rearranged to give you 1 cross 1 cross 400. Fine? Okay. What happened in this case? You have to help me out to understand this again. What is this 1 cross 1 doing? If you are doing 1 cross 1, same is not needed. क्या कर रहे हो? So dimensions are this plus this minus 1, so that gives you 1 cross 1 cross 400. This is fine. This, what will be the size of this guy? 1 cross 1 cross 400. Okay. And how many of them will be needed to get this? 400 of them. So how many total parameters? 400 cross 400. Same as here, right? So this is again same as this operation, nothing special is happening there as well. I want still more arguments to convince that they are actually the same. So what will this one volume do? 1 cross 1 cross 400. Every number will get multiplied with those numbers, right? So, and then that gives you finally one number. This is what happens here. Everybody will get multiplied with weights to give you just one number. So exactly same operation is happening. So we have got an equivalence between this and this, this and this. What about the last one? Last is same. This was 400 cross 400. Now this is 400 cross 4. So what will I need here? 1 cross 1 cross 400. That means to get one number I am multiplying 400 numbers with weights. To get one number I am multiplying 400 numbers with weights. Same operation. So all we have done in this slide is something. We started with a convolutional neural network, and then at some point we flattened it out, we turned it into a vector, and then finally did the good old feed forward neural networks, right? Feed forward and fully connected. In this case, you are doing convolutional neural networks. The property of convolutional neural networks is that they are sparsely connected and parameter sharing, right? So until now we were doing that. If you see in this part, those properties are lost, right? Nothing is sparsely connected and nothing is, there are no parameter sharing. So basically that's why they are equivalent to this. Right. कहाँ पे? See, this my vertical line is telling you where flattening is happening. So these 400 numbers I flatten to get a vector of size 400. These 400 numbers I rearrange them such that it is still a volume of size 1 cross 1 cross 400. No parameters here, no parameters here. See, this is a rearrangement, this is also a rearrangement. That's it. To go from here to here? No. To go from here to here? No. Here we had 400 cross 400 parameters plus biases. Here we have 400 cross 400 plus biases. So we have not talked about the number of biases. How many biases here? How many biases will be here? As many as number of filters, and number of filters are 400. So these are the exact same operations. More questions here. This and this. That question lies here. Why do you need two hidden layers of size 400 and 400? This is your choice. I mean, you will see many papers 4096, 4096, 4096. So that's what we said. So once you have fully connected networks, there is no parameter sharing. Parameter sharing ended here only. So what we are saying here is, we thought I can convert a fully connected or a neural network to CNN by applying parameter sharing and what was the other thing? Sparsity. Okay. In this case, what we are saying is, there is no sparsity, there is no parameter sharing, I can still convert. More questions here. None? This is important to understand the next slide, because there I will be fast. So if you have more questions, ask it here itself. And there we will have something else to understand, so better you understand this concept here itself. All we are doing is, instead of looking it as a vector, I am looking it as a volume. That's it. Nothing special. This is the only thing to catch here. Instead of treating this as a vector, I am treating this as a volume. That's it. Okay. So now you have to explain me what is happening here. Don't look at three of them at once. Just look at the first layer first. This is fine, nothing special here. So 5 cross 5, this was 14 cross 14 cross 3, 5 cross 5 cross 3, that will give me 10 cross 10 cross 16 if number of filters are 16. So now I do max pool over a 2 cross 2 thing, that will give me 5 cross 5 and will not touch this guy, so this is fine. Now fully connected, what are we doing here? Instead of doing this part as we were doing before in all the networks, what we are saying is, don't do this. Okay? You are still doing fully connected 5 cross 16. So what are you doing here? 400 numbers. This is same slide as before. वो जो bottom वाला जो next वाला network था. So 5 cross 16, 400 numbers. It is not flattened. You have just rearranged to give again a volume. This volume is of size 1 cross 400. How many parameters here? Parameters is 0. Okay, because it's just a rearrangement. Now 1 cross 400. What was this? 1 cross 400. How many of them? 400. That gives you this guy. Now fully connected. So what is 1 cross 400? How many of them? 4. How many parameters will be here? 400 cross 4 plus 4, right? And you will get that in that vector version as well. You will get exactly the same, 4 cross 400 plus 4. So is this fine? So we were used to see a softmax like this vector, but now we are writing it as a volume and nothing special. Okay. Tell me what happens in this particular thing. Chalo. Yes. What happens in this? padding. This is not padding, but that's okay. What is, see, 14 cross 14 cross 3, we know how it is going. Okay. So you have now written this 16 cross 16 cross 3 image. So you have written this 16 cross 3, 16. So this was 14 cross 14 cross 3. You know all the math, including all the parameters. This is 16 cross 16 cross 3, and I want to use this one to do something here. What is this? 5 cross 5 cross 3. How many of them? 16. Now tell me, why blue strip and why yellow strip? Blue strip is exactly same as this one. Okay. So blue strip is this. We keep this blue strip. Max pull 2 cross 2. You have to help me go here. First of all, why 12 cross 16? 16 filters. 16 minus 5, that gives you 11, plus 1 gives you 12. So if nothing is mentioned, we go to original convolution that we had done. Or else you will have to mention what are you doing in the convolution operation. So 12 cross 16 is fine. This was 10 cross 16. This is 12 cross 16. I want you to see that this 14 cross 14 is exactly same as this here. Everybody gets the question here? What I am saying here is, this is 16 cross 16 cross 3. If you remove these yellow strips, this is 14 cross 14 cross 3. You do the convolution operations. The claim here is, when you do this convolution, you get 12 cross 16. This 10 cross 10 cross 16 is same as the original 10 cross 16. What new you get are these yellow points. And similarly here. So I should have asked you this question here itself and not here. Yes. Apart from these numbers will be the same as before. Why? And this is super easy. So if you think this is difficult, no. 5 cross, so let me take a different color. 5 cross 3. So let me not do this one. So 5 cross 3, there is this volume, right? Just because I added these yellow numbers more, will it have any impact on these computations? So you run it over this or you run it over this, those computations will be independent of these blue guys. I mean, sorry, of these yellow. Check it out. 5 cross 3, number will be same whether you do it here or here. Yes or no? Questions? How many of you are not with me? Okay, how many of you are with me? Okay. 5 cross 3. Those same numbers. So right now we are saying ki 14 cross 3, you copy paste here. And then these yellow numbers, you add more. So the dimension of matrix is now 16 cross 3 and not 14 cross 3. But the sub part of it, which is 14 cross 3, is actually the original one, this one. What I am calling original is just the previous one. Okay. So the new numbers are these. How many total new numbers are there in this volume? How many total new numbers are there in this volume? Total new numbers, how many? Right, so that was the right answer. 16 cross 16 cross 3 minus 14 cross 14 cross 3, whatever that number is. Okay, so I want you to just visualize one thing, that these these yellow things, they also have 2 layers because this is cross 3. So you will see a depth for yellow ones as well. So total numbers of visible yellow numbers cross 3, that many extra you have added. Fine. Now this is my 14 cross 14 cross 3 original blue one. You take this convolution or you take the second one, right? Will adding these yellow numbers have any impact here? No. So this whole thing that you were doing here, you can continue doing here. It will not impact this. So my first 10 cross 10 will be just these guys. Is that okay? Right? What new will come is because of these blue guys. What new will come is because of these yellow guys, and they will not start playing a role until one of them will fit into my this convolution, right? Until they come into here, they won't play any role. My numbers will be same as before. So this blue part is same as this guy, but I have introduced new numbers, so of course because of them new numbers will be there. Is this fine? Now the same thing will propagate all the way. So this guy goes here, this becomes 6 cross 6 cross 16 instead of 5 cross 5 cross 16, but these 5 cross 5 cross 16 are same as this. Make sense? Okay. Now you do the same thing again, and this time when you are left with 2 cross 400, right? This blue remains same as, so this volume, so how many numbers will remain same? 400. 1 cross 400, but remaining 3 will be different. So you have 2 cross 400 here. Now you do 1 cross 1, so what will be the specifications here? 1 cross 400, and how many of them? 4. Okay, and then finally, so same operations are being done, and finally you have this. This will be 4. This will be 4 because this was 1 cross 4. Okay. Thank you. Yes. ये 400 किस एंगल से लग रहा है? Yes. So is this 2 cross 4 fine? Okay. What happens in this case now? So instead of 16 cross 3, you have now made it 28 cross 3. You have to finally tell me how are you getting this 8 cross 4? Exact same thing. So tell me, you just added 2 here, and this actually became 4 times, whereas you have doubled here, and has it increased by that factor? Anyway, bad question, does not matter, leave it. So this is 28 cross 3. You will have 14 cross chunk here. That will give you how much? 1 cross 4. This 14 cross 3 will give you 1 cross 1 cross 4 there. So tell me why 8 cross 8? You will not shift 8 times. Stride is just 1. So what is creating that difference? Okay. But so
We can say that there we increase from 14 cross 14 to 28 cross 28.
right.
We have added 14 more.
Exactly. So you have added 14 more columns here and rows here.
So half of that size will increase there.
Right. Because you are doing max pool. (14 cross 14 cross 3), that will give me 1 cross 1 cross 4. So this whole thing will give me 24 cross 24 cross 16. So if you go this way, will you understand? I'll let you do that then. Okay. So finally I'll get 8 cross 8 cross 4. So what is happening? What did we learn in this slide? Particularly this second one. So this is the most important one.
We can have a window which will have at its own value at the end. Like we can have any size of the window, and we can do with the value of filters, so we can get the specific values for each window. Like in this case, we are having a window of 14 cross 14.
Right.
For each 14 cross 14, we have one cell in the end.
Right. So what is happening in this case? Where does this, so question, where does this, what is which color? Green color belong to? There. In 16 cross 16 cross 3, where does this green color gets mapped to? Yes. Last window. So it is these last 14 cross 14 cross 3. Yes or no? Right? Where does this one gets mapped to? So let me keep it red. Where does this map to? This left 14 cross 14, and the right one is just the last one remaining, right? So this one. Okay, is this fine? Tell me, how does this help us in sliding window protocol now? If my image is of size 16 cross 16 cross 3 and my sliding window is of size 14 cross 14 and cross 3, I don't need to run this 4 times. Look here. What we were doing? Keep your sliding window here, shift, do classification again, shift, do classification again, right? What is this telling you? So if let's say this is 14 cross 14 and if let's say this is 16 cross 16, let's say this is 16 cross 16 cross 3, and let's say my window size is 14 cross 14 cross 3. Actually this one is not needed, we just need the face. So 14 cross 14 cross 3, this guy and this guy and this guy and the last one, right? You don't need to run. You can just in one computation compute all these 4 classification values. Is that fine with everyone? कुछ ज़्यादा ही गड़बड़ बनाया मैंने, but let me try to do it better. So this is my first 14 cross 14 cross 3. Then I have, so this color was originally blue, and then you had green. And then you had, I think, let's keep it. What happened? What did we gain here in this case? I don't need to shift these windows 4 times. And why I am okay even if I don't do this? Because you see, all these guys, that is common to all, there my computation of convolution will be same for all these 4 windows. So why repeat them? Okay. So finally what we get is this one. Questions here. Right. So is this fine? So convolution implementation, right? Just by not writing vectors here and by simply keeping writing volumes, we have decreased a lot of computation. In one pass you will do this, you will get 4 and you will get 1 cross 4, and in the same pass here with increasing little bit of complexity, you will get 2 cross 2 cross 4. Okay, and computational complexity has not increased much because of these guys. You are not adding too many things. Whatever little adds gets added here. Any questions here in this? Yes. It has reduced already. Dekho. You computed this one. When computing this one, you've already so see. So the question is, how have we reduced? First, you will take this window, compute this whole thing. Okay. Then you take this window, compute the same whole thing. Yes or no? Done? I guess so much? Okay. Okay, so convolution implementation of sliding windows actually help us. So if this is 28 cross 28, right, let's remove that 3 part. I think that's what they've done. So if this is 28 cross 28, the same old thing you get 8 cross 8 cross 4. So you don't have to iterate this so many times. Final one volume will give you all the predictions. So what is there in this 8 cross 8 cross 4? How many predictions will be there? How many predictions will be there? What is this output 8 cross 8 cross 4? What will this first, so 8 cross 8 cross 4, that means it's a volume whose depth is 4. So can you help me figure out what will this first volume give me? How many sliding windows here? How many iterations of sliding windows here? If this is 28 cross 28 and my window size is 14 cross 14? 14? 30. How come? Right, 14 cross 14. Okay, in one direction it is 14. है ना? हाँ. So you run these many and what will you finally get? So what is this 8 cross 8 cross 4? How many predictions are there? 8 into 8, 16. Sorry, 64. So you have 64 volumes, each one is a softmax, right? So each one here is a softmax, giving you the probability of which class is there in the first one, second one and so on. Huh? क्या हुआ? नहीं समझा? Right? So you don't have to run those things again and again. That was the point. Now tell me, how will this work with a very small sliding window? So I want you to give me how does this spectrum work. Full image size versus 1 pixel. When you keep just 1 pixel as your window size, does this give me any advantage? No, because there is absolutely nothing common between two windows. So whether you do it individually, whether you do it in a convolution fashion, it will not matter. It will only help you if there is more and more overlap. But if you overlap the window size with this whole image, then basically you are just doing classification. If in your object you have more than one classes, so if in your image you have more than one class, you will be able to detect only one class. And there is no detection at all, because if this is my window size, I will be able to say yes, there is a car, but where is the car? I won't be able to tell you, because there is only one sliding window, which is this one. So sliding window has its own role, but sliding window is nothing but a fancy application of a classification algorithm. You are not doing detection here. Somehow jugaad karke, which is complete deep learning is jugaad, but this is next level of jugaad, right? So you are given an image and you are trying to solve classification, but because you are moving sliding windows and depending on which sliding window gets the object, you will say object is here and it is car. So you are telling me both the things. Object is here and the object is car. Questions here? Okay, so we are done. Bounding box predictions, accurate. So how do you accurately predict bounding boxes? We'll talk about YOLO now. Okay, so this was just the sliding window protocol, and now we'll talk about YOLO after the break.